We have already studied rectangular waveguide filled with a dielectric material. The question now is, what will be the situation if the waveguide is partially filled with dielectric material? It means that we have a dielectric material of epsilon equal epsilon r epsilon naught, which is obtained or can be found longitudinally along the length of the waveguide from x equals 0 to x equal t, and then the remaining part is free space, for example. This is called partially loaded waveguide. Effectively, partially loaded waveguide has many applications in attenuators, in phase shifters, and also it is used in the case of the ferrite material to develop ferrite loaded waveguide structures, especially in the case of isolators, for example. So we have many applications with this configuration. To solve the problem in the general case for partial loaded waveguide, it would be quite complicated problem. So in the present case, we are going to be limited only for transverse electric mode of M0 mode. M0 mode, it means that we have M variation in X direction, but we have zero variation in Y direction. Zero variation in Y direction, it means that it is constant in Y direction, means that the derivative with respect to Y would be zero. So Helmholtz wave equation in this case would be only depending on partial squared by partial x squared, because partial by partial y it would be zero, assuming that we are talking about transverse electric M0 mode. We have zero dependence on y. Okay, and because there is no transverse magnetic M0, we are limited to transverse electric. Okay, for transverse electric M0 mode, we are looking for magnetic field Hz in the magnetic field in the longitudinal direction Hz. The Helmholtz wave equation in this case would be depending on epsilon r at x from 0 to t, and it would be depending on free space from t to a. So the Helmholtz wave equation would be separated in two equations, one for x greater than 0 and less than t, and the other for x greater than t and less than a. In the first equation, the propagation constant beta would be square root epsilon r k naught squared minus kd squared. While in the second section, or in the free space section, the propagation constant would be square root k naught squared minus ka squared. In both cases, the propagation constant along the z direction should be the same. This means that the propagation constant in the air space or in air bar should be the same propagation constant in the dielectric bar, such that the phase in both layers should be continuous. This means that we have a coefficient kd squared for the part of the dielectric, which correspond to epsilon r k naught squared minus beta squared, and ka squared in the air part, which correspond to k naught squared minus beta squared. Okay. Now, the differential equation in the present case has two parts in two different spaces. This means that we have two different solutions. One solution for the region from x greater than 0 and less than t, and the other solution for x greater than t and less than a. Okay, and effectively this differential equation, the solution of this differential equation is sine and cosine. So in this case, for the first region, it will be a cosine k dx plus b sine k dx. The other equation, it would be c cosine ka a minus x plus d sine ka a minus x. Should be noted here in the second equation, we prefer to make the coordinates start from the point A, not starting from the point 0, such that we are starting from the boundary at the right, while the first equation starts from the boundary at the left. There is no problem at all if you are assuming that it is cosine kax and sine kax. It will be some sort of transformation of coordinates in this case. So we are preferring to use this solution such that the second equation is mainly depending on the boundary condition at x equal a. Okay? Alright. And to be sure, let us first check if this equation is satisfying this differential equation or not. Here, if I'm differentiating this with respect to x, the differentiation of cosine, it would be minus sine. And because this is minus x, it would be plus sine or plus ka sine ka multiplied by a minus x. Okay? Now if we differentiate once again, this sine, it would be cosine. And because we are differentiating with respect to x, it would be minus. So we have minus ka squared sine, so minus ka squared cosine ka multiplied by a minus x. So the second derivative would correspond to minus ka squared of the same function. So the differential equation is valid. Alright? Okay. Now it is required to apply the boundary conditions. To apply the boundary condition in the present case is the tangential electric field at the perfect conductor. It is 0. The tangential electric field in this case, it would be Ey at x equals 0 and Ey at x equals a. At x equals 0, we are talking about the first equation because the first equation is from 0 to t. At x equals a, we are talking about the second equation because the second equation is at x from t to a. So the electric field Ey in terms of Hz is j omega mu over kc squared partial Hz by partial x. So it would be j omega mu over kc squared. Here it would be kd or ka. Kc would be kd or ka. Partial Hz would be, this cosine would be minus sine and this sine would be plus cosine, and we have kd and we have kd squared, so it would be kd in the denominator. In a similar way, here the differentiation of the cosine, it would be minus sine, and already we have minus, so it would be c sine ka multiplied by a minus x, and the derivative of sine would be cosine, and we have minus here, it would be minus d cosine ka a minus x. Now by applying the boundary condition, that is the tangential electric field Ey at x equals 0 is 0. So at x equals 0, this term it would be 0 and this term it would be unity. This means that the value of b should be 0. On the other hand, at x equals a, sine a minus a it would be 0, cosine k a minus a, so it would be 1. So in this case, the value of d must be 0. So from the boundary condition that ey equals 0 at x equals 0 and x equals a, we obtain that the value of b equals 0 and the value of d equals 0. This means that the remaining part hz is a cosine k dx for x greater than or equal 0 and less than or equal t, and hz equal c cosine ka multiplied by a minus x for x greater than or equal t and x is less than or equals a. Okay, that's what we have. We still have another or other two boundary conditions. The other two boundary condition is that the tangential electric field at the dielectric interface at x equal t or t minus should equal the tangential electric field at x equal t plus. So in this case, by substituting the value of x by t minus j omega mu over kd a sine kd t should equal j omega mu over ka multiplied by c sine ka a minus t. And by eliminating j omega mu, because it's the same, here we have minus a over kd sine kdt equals c over ka sine ka multiplied by a minus t. The last boundary condition is that the tangential magnetic field at t equal t minus or at x equal t minus should equal the tangential magnetic field at x equal t plus. And it should be noted here, Hz is tangential to the plane x equals t. So in this case, the value of a multiplied by cosine kd multiplied by t should equal c multiplied by cosine ka multiplied by a minus t. This is the second equation. It should be noted here that we have two equations and two unknowns a and c. In addition, we also don't know now the value of ka and kd. So by eliminating the coefficients a and c, this can be done by taking or by formulating the problem as a matrix multiplied by a and c, vector a and c equals 0. So in this case, to obtain the values of a and c, the determinant of this matrix should be 0. The determinant of this matrix in this case is effectively the characteristic equation of this partially loaded waveguide. And this characteristic equation, it can be obtained assuming that by dividing equation 1 over equation 2, we are going to eliminate a by a and c by c. So sine kd o t over cosine kd over t. This is tan kdt. So the first one is minus 1 over kd tan kdt equals 1 over ka tan ka multiplied by a minus t. By multiplying this by ka and multiplying this by kd and getting this term in the other side, we can obtain the characteristic equation as ka tan kdt plus kd tan ka multiplied by a minus t equals 0. This is the characteristic equation of the partially loaded waveguide, and the relation between Ka and Kd, it can be obtained from beta. Beta equals the square root epsilon r k naught squared minus Kd squared, and also equals square root of k naught squared minus Ka squared. So we can, by getting this beta squared, we can obtain Kd squared as epsilon r k naught squared minus beta squared, and Ka squared as k naught squared minus beta squared. So we can replace all this equation in terms of beta only. We are going to replace Ka by square root of k naught squared by beta squared, and we are going to replace Kd by square root of epsilon r k naught minus beta squared. So this equation would be nonlinear equation of beta. By solving this nonlinear equation of beta, we can obtain the value of Ka and Kd, and from the value of Ka and Kd, we can find the ratios of the value of A to C. So we can obtain the field distribution inside the dielectric medium and inside the free space part. This is how to solve partially loaded waveguide for transverse electric M0 node. Alright? Actually, we are going to use this problem in chapter 9 for solving the problem of isolator. Until this, let us keep this in our mind now. Alright?